For my neuron model, I took one from a published study. So it was one that one group has spent a long time creating and creating it as accurate as they can. And so here's the cell model, and it's composed of all of these .hoc or .mod files. Basically, it's written in the Neuron software, so we can check those out. And these are all just different files for building the mechanisms of the neuron. It's a Hodgkin-Huxley, modified Hodgkin-Huxley model. It's got about a bunch of 17 different types of ionic channels and mechanisms that it uses to simulate for the cell. And it's got a complex morphology. You can see the connection data here. Basically, this group spent a long time developing this cell, and I'm going to use it here to measure the activation response. And this is a CA1 pyramidal cell model, so it is perfect. And here you can see the morphology of the cell that we're using. And so I wrote some Python code to extract that model and basically move it and shift it, put it inside a .model file. And then what I do is I've taken those, I want to find the coordinates of each compartment of the cell, because I'm going to take that and extract the voltage at that location from the results that I just showed from my admittance method simulations. And then I'm going to write some neuron code to basically run a simulation with the cell with a mechanism called an extracellular voltage applied, which basically applies the voltage from the admittance method onto the membrane of the neuron, and that should affect the neuron's response. And then we'll vary the amplitude of the applied voltage, and because this was an entirely resistive model, we didn't include any capacitance in the tissue model of the hippocampus. That means that we should be able to linearly scale the voltage with the current. So at the end, once we determine what voltage is required to obtain the desired response from the cell, we can go back and say, okay, well, this current needs to be input into the electrodes given that this voltage is required.